reactivity, but they help draw them and arrange them and orient them so that they are in a position to be a very good nucleophile. So remember that we're showing the chemical reactivity is very simple on this, very, very simple. But remember, there's this greater framework that plays a huge role because it's very dynamic. And so shifts in the structure can make it even more basic or acid because it changes the environment, right? As we shift the structure, you can imagine changing and shifting things. So that's something to remember kind of practically, that you can now understand, okay, this is not a system like I'm used to working in general chemistry. It's much more dynamic, and it's a much different environment than just bulk, buffer properties. Yes.
You're starting like that a beta or a
this one. Yes, this is what we consider a beta 1,4 linkage, right? Yep, that's right. If I had drawn this down in a down position, then that would have been an alpha 1,4. So the anomeric carbon, right? This is the anomeric carbon. This one is not. This does not open up. The anomeric carbon determines what kind of linkage it is. If it's down, it's an alpha 1,4 in this case. Or it could be an alpha, what's the other type we see? 1,6. Right? That's the branch points. Okay, so we typically see linkages between the 1 and the 6 or the 1 and the 4. Those are the most common. So does anybody have any questions? It's a very beautiful, I mean, it's amazing chemistry, and it's amazing that it works, right? Because you're like, oh, that's not a great case, right? But in the active site of an enzyme, it is. It's amazing. It's really amazing. And it's very simple. This makes organic chemists jealous. It's like, they could never do this reaction in this simple fashion. They have to do, jump through hoops to do what enzyme does very efficiently. I know I'm getting down my path. Does anybody have any other questions about that? If that's as simple and as hard. Now, what if I said, okay, here's where Dr. Patterson gets tricky. Okay, there's an enzyme. All right, there's an enzyme. And it has the same active site residues. You discover that it has the same active site residues as lysozyme. Okay, I could pull a problem like that. It has the same active site residues. I'm just going to draw this out here where it's easier to see, as lysozyme. But it catalyzes a reaction with a different substrate. Okay? And so I could do something kind of crazy, but it's not that far-fetched. But I could say, okay, we have this unique compound. Okay, it's an aromatic compound, okay, and it is linked, okay, to, let's see, just making something up, a 5-member ring, okay, and this might have some kind of unique functional groups like that, okay, and all I tell you is there's an enzyme that uses this substrate, and I'm just going to call this enzyme. And it performs this reaction. The cleavage, okay, of this 1,4 kind of phenol, right? Phenol alcohol 1,4-hydroxy phenol. Okay? Plus, and then it makes something that looks like this. All right? And I say, okay, I tell you, it uses same mechanism as lysozyme. Okay, so what do we know? Okay, here's the bond that's breaking. Looks very similar to lysozyme, right? It's got kind of a glycosidic-like linkage. It's not too sugared, but we have two ring structures. And I said, show the mechanism for this compound. You can do that. And that's why we learn these mechanisms, because when you learn one mechanism for an enzyme, you can apply it to a lot of other enzymes because they use the same strategies in a lot of their synthetic methods. So what would we do? For this enzyme, right, we would put that into the active site. Then we start to do our air push. We know it has to get from that point to that point, and we know the mechanism has to be the same as what, or it uses the same functional residues as lysozyme. So what do we get? We're going to get attack here, right? On breakage, we've got that passive assisted, right? On cleavage. And we know that this could be right? And now we have our deprotonated glutamate, right? And we have our link aspartate. Now what? Using water. So water, and the water comes in here, and we do the same thing. Pull that off, that can attack there, right? That goes back. And by learning that mechanism, you can apply it to many other enzymes because while nature is clever, it uses a lot of the same strategies over and over again, okay? Which is cool, right? Something works really well, there's no need to improve upon that. Right? It's a new color, don't be confused. So you've learned now how you can apply the same mechanism to something else. In lysozyme, technically, yes. I would, yeah. In lysozyme, it has to attack that specific ring, because that's where the specificity is for. Yeah, technically in this one, couldn't you flip it around? Yes, you technically could. This is probably the more reactive part of this molecule. But if I lay it out like this, then if you have no way of distinguishing, you might as well just draw it out that way and stick with that bond. Right? But you get the idea. And if I specify which bond is actually being broken, but yeah, either one could be equally done, but there has to be specificity for one or the other. It cannot flop because the binding pocket, right, has a specific conformation and arranges those molecules in a specific fashion and does a reaction on a specific site. That's what somebody asked me, why doesn't the enzyme work on something over here? It's because those amino acid residues are positioned at just the right point, and the binding is to bind and lock those substrates in just the right way so that it cannot react with all the other things. Yeah, in this case, yes, you could. Yes? No, I would not give you, not for this, I don't even know what this is called. And organic chemistry is not my biggest strong subject. So I would give you a structure and so that you can see it, right? And that then you could say, oh, I know that looks like this. I'll apply the same principles that I've learned to something else.
But are you gonna tell us what comes up? So it's not like, like, or are you just gonna draw it and be like, well, this is, you should know this is, or it's a cyclic discussion?
No, I always ask you, I have to specify the enzyme or it doesn't, you can't determine anything. There could be 1,000 different types of enzymes, right? I have to specify what enzyme it would correspond. All right, that's it. I'm grilling you here. Is it gonna be this? Or my favorite one that people use it. Have you even written the test yet? Does it matter? Yes? Because I'm here not to learn, I'm here to siphon up information about what's on the test, right? Okay, so we're good with twice design, right? And now we want to do So, what's in the active site of the phenolates that's unique? It has broad chemical capabilities because it has something. What does it have? Magnesium has. So we have magnesium plus divalent.
I've been eating all day.
Very important moles. Very metal catalysis. And we have our substrate. Okay, I'm going to show it. I like to draw it. Let me draw it in there. This guy.
He's doing it anyways. Yeah, because it has a hot
So if we remember, where do we have to get to in this reaction? So this is like DPG, right? Phosphoglycerate to phosphoglycerate, right? Is that right? Something like that.
because it was some negative oxygen.
It's got a phosphate in the 2 position, right? And it's glycerate because of this structure.
Yeah, it would have to be.
We good with that? Yeah, okay, sure. That sounds good. You're the teacher, come on, you tell me. Okay. And we want to get to this position where okay, well, we get to this, right? Enol, right? Phosphoenol. 2-phosphoenol. I forget what the exact name of this is. Not important, right? Phosphoenol pyruvate. Very good. Phosphoenol pyruvate. Okay. It's important intermediate in glycolysis, which we'll learn about later. So how do we do this, right? There are important amino acid residues on the enzyme. I'll draw those in blue. We have a lysine. I'm not going to draw out the whole thing, but that's all we need to know. There is a lysine and there is a glutamate, right? There's a whole Yeah, I'm sure. I'm just checking because I'm losing some stuff. So, just making sure. Okay, so what happens is this magnesium coordinates to the carboxyl group. And you immediately see what's going to happen here. We have to get something basically hydroxylated, right? And that's very hard. We got to break a hydroxy bond, right? And how do we do this? Well, we have these magnesium ions that coordinate to the oxygen, and they stabilize that, but remember they stabilize the transition state better. And the transition state is where this is going to have both of these oxygens negatively charged. We've got a fairly strong base here, right? And we've got an acid. So this is all acid-base catalysis assisted by these metal ions. So what happens here, let me get a different color. Blue, green, hopefully not even colorblind, but this grabs that proton, right? It's a good base, okay? These shift up here, right? And the electrons flow to the electronegative oxygen, right? And these positive charges are helping to draw that, right? You could think of these as your electron sink, right? Whenever we see positively charged things, usually electrons start to flow that way. So you could think about these in that fashion as an electron sink, where the electrons flow to the magnesium, right? They don't get taken by it, but they flow that way, okay? And so this leads to our next step. And now we've created a monster. Now, I decided now we've created this intermediate, very high energy, right? You have two negatively charged oxygens, okay, on here. E03 minus, right? And we still have our hydroxyl here, right? Nitrogen. Right? And then now what have we got here? We still have the magnesium, it's doing their job. Plus, sometimes when I talk, I feel like Bob Ross, drawing having the tree. What's that? You have the knees down, right? All right, so it's been a long day. It's been a long day for you too. You haven't figured it out. You probably never will. That's okay. I love it. Okay, so we got to that position, right? We're almost there, but the double bond's on the wrong side, right? So we got to kick this off. So something's got to happen, right? Electrons are going to have to flow back, and we've got to make that a good leaving group. We have the acid there to help assist, right? So that can donate that proton, and that's exactly what it's going to do. Okay, it's going to, this is an acid-assisted catalysis, so I like to draw it this way. This is the way the book does it. The electrons flow now towards that proton, releasing it, okay? And in the end, that's what we get out. And I don't draw it regenerating the active site because I'm not sure what the exact mechanism is. I can give you conjecture of what it is for this enzyme, right? So we end up like this. Lysine, and we have draw it this way. This helps you. There's our glue, right? We haven't regenerated the active site. We still have this, but this glutamate and this lysine are in close proximity. So what I think probably happens here is we just have an exchange between these two, all right? And then that would regenerate the active site, right? And if that helps you, I do not expect you to know that because I am not sure if that is the exact way. There could be other intermediaries here that are involved with that exchange. But that's one possible way to do that. Okay? Yeah, that's fine. That helps me understand it, but I'm not sure if that's the exact way. There has to be some way of regenerating because it has to be able to go back to its original state. Catalysts are not consumed by a reaction, right? They just help speed up the reaction. But it gets us back to that original position. Does anybody have any questions about that?
We can stop there.
Yeah, you can stop here. You can stop at this, not the arrow pushing. You can stop at that. I want us to know how does it do the reaction. All right.
So the dots with that reason.
That's I'm showing the bonding, right? Non-covalent ionic, electrostatic interactions, right? With the oxygen. This oxygen is negatively charged, definitely will interact with that. This has a partial negative charge, right? It's more electronegative than carbon. But in this state, yes, and I can draw that, right? It's going to associate. That's what I mean by those dots. Is that it's coordinating to.
Yeah, I was just wondering if we have to.
Is that hard to do? Okay, they do it. Okay. So next one, serine proteases, and they all work pretty much. All serine proteases use the same catalytic triads. That's why I started out when I talked about it. I didn't go right to chymotrypsin. I didn't go to trypsin. I went to serine proteases because as a class, okay, these enzymes are all the same in the residues that carry out the reaction. In close proximity to the aspartate, and then my green is going to be like hydrogen bonding, right? I can share that. Histidine, right? And then we have a serine, right? So that is the active site of the enzyme. And we know all of these serine proteases are proteases, so what are they cleaving? Cleaving peptide backbones, right? Peptide bonds, amide bonds, right? And so substrates for this, draw this slightly different configuration. I'm just going to draw it in a linear way to make it simple. Alpha carbon, and I'm just going to call this R1, right? C.
Doesn't have to be the adult.
It's on the left.
Get 'em.
We're drawing the Fisher projection, right? It should be all on the left because they're all L, right? R1, R2. And then I'm just going to draw this. Like that. We know that is the rest of the bond. Okay? And so, if I said this enzyme were trypsin, okay, what would R1 be? if I said this enzyme here were trypsin, what would R1 be of this peptide? Where does trypsin cut at? On the C terminus of positively charged. So R1 will be lysines, arginines, right? That's where its specificity is, okay? If I said it were, so arginine would be equal to K and R. If I said it was chymotrypsin, then it would be aromatics, right? It would be phenylalanine, it would be tryptophan, it would be tyrosine. Okay? And so, what if I said an aspartate amino acid, or protein, sorry. Yes? Yeah, N-terminal side of aspartate, so that means R2 would be equal to aspartate, right? Because it's on the N-terminal side of aspartate. So you see, they can have different specificities. So in aspartate, there would be a specificity pocket for this R2 group. Whereas for trypsin and chymotrypsin, there would be a specificity pocket that would specifically bind to residues, either lysine or arginine in the case of trypsin, or for chymotrypsin would be one of aromatics. But that's the only difference. They all cut the same backbone, but they have different specificity. And if I could just take a step back, how does that work? If I could ask you a question, why they do the same cutting, right? What is it about that specificity pocket that allows it to only cut after these residues? Who has an answer to that?
Is it the interaction between the residues in this?
Yeah, it's the binding affinity, right? The enzyme uses binding affinity to help lower the activation. And to have binding affinity, you have to have enough interactions to lock it down. So the enzymes have to overcome the same energetics, okay, to bring them in, right? They have to overcome this entropy, right? They have to provide enough body energy. And the specificity pocket, right, helps to bring it in and draw it in and lock it down. That's probably more than you wanted to know today, but that's a good thing to really understand how this all works. Okay, so let's get on to the business here, right? Okay, so what happens here? Let's just say this is, it doesn't matter which one it is. Let's just say it does this. It's going to clean this bond here. So what happens? I'm going to use my colors. Okay. This is a base, right? Histidine acts as a base, helps convert this to a nice alkoxide, very nucleophilic, right? And we have this amide bond. This is carbon's partially positive charge, right? And we've got the electron withdrawing oxygen, more electronegative, so it makes it susceptible to this nucleophilic attack. And then what do we get? We get this tetrahedral intermediate transition state, very high energy. Okay? So let me draw my, oops, that's not right. Do a bit of carbon bond there. So I've got serine that attacked it. Our histidine now is protonated. Remember, this is still interacting with aspartate. Aspartate doesn't really do any of the reaction. It helps orient the histidine, okay, and it helps delocalize the charge over the histidine, right? Helps make it a better base, okay, and so it's involved in modifying the electronics of the histidine, manipulating it because of its close proximity. But largely it helps to also orient it and lock it into position. It also affects its electronics, though. So I'm not going to draw the aspartate in it. If you do that on this test, that's fine also. I'd like to see them at the beginning and at the end. Okay, so now we have this. R2, okay, C, R1. We have this tetrahedral intermediate, very high energy, right? So this would be the transition state. This is what the enzyme stabilizes, finds best the transition state. This is still high energy, still very unstable. It stabilizes it long enough for it to now go into a product, right? So what happens here is we can have our electrons, right? This is high energy. These electrons want to fall back and make something that's more stable. What am I using? Okay, so they will do this. They will fall back here. This is a base. I know this is kind of confusing, but this will grab that. It's base assisted, okay? And we will regenerate our histidine, okay? So let's draw our histidine. Start drawing different kinds of configurations. Okay, so our N has left, right? That's gone. Now we have our serine. And now we have our regenerated histidine. It's 3 lone pair of electrons, okay, and then we have now what left here is our NH2, C, R2, whatever was attached to it, right? So that's what left. That piece was cleaved off, right? And now we have this, a covalent intermediate, right? And how does this work? Just like what we saw with lysozyme, right? Enzymes aren't too tricky. They use the same thing. It's a hydrolysis reaction. There's water around, and so water comes in, right? We've got to regenerate our enzyme. It makes this a good hydroxyl, right? Everything flows to that oxygen, that electronegative oxygen. Okay. And we make, again, the tetrahedral intermediate. R1. And now we have serine here. We have our hydroxyl. Regenerated histidine. Still interacting with the aspartate up there?
Yeah.
Oh, yes. I forgot my step here. There we go. Thank you. And so now we've done that, right? We'll regenerate the histidine here in just a bit. It'll have to back up. Okay? So we get this tetrahedral intermediate, high energy. Everything's got to fall apart, right? And what's the best leading group? This is going to be the best leading group. It breaks this, grabs that proton from histidine. The electrons flow back to the nitrogen. And our product leaves, so we have our COOH, right? C1 that leaves, and now we have regenerated. Oh, I'm sorry about the blue going to red. I don't know what happened there. Serine. Still hanging out there, right? And that's it. The deal is it has to go through 2 cycles, right? 2 tetrahedral intermediates, one, right, that leads to bond breakage of the amide backbone bond, right? One that leads to breakage of the enzyme linked intermediate.
Oxygen.
It's like Histidine is studying everything.
Histidine is a very important player. So histidine's a major base, and its pK is around 6, right? So it's right around neutral pH where it does all this stuff, right? And so, you know, slight shifts in the pH, right, can shift it from being either acidic or basic, very simply, right? And it's right around in that area that is physiological pH. So it can act as both an acid and a base, relatively simply, right? Does anybody have any questions? Oh, serine, it grabbed the proton back from histidine. Yeah, let me, should have. You got it? Yeah, the OH, yeah, it came from the water, yeah. I draw them close. I don't know. I draw big, and then as I get going, right, I'm kind of like a choo-choo train, you know, loud, and then it goes by, and it's like it's smaller and smaller. It's a big like this. Yeah.
The first product, did it just take up an extra hydrogen?
Oh, this one?
Yeah.
Oh, it would actually, if we drew it out with all of this,
It actually had one.
that's what it would look like. So it's picking up that. I should have drawn this as NH. You want to know where they come from, and then one of the H's would come from protein, right?
If we don't put that on our test, we can.
Oh, absolutely. Yeah. No, I don't care about it. NH2, it's fine. And if you don't do it color coded like I do, I'm really gonna hammer you. You know, like color coding is like 90% of the score.
What is this, psychology?
So if I see lots of, I tell my students in my lab on Tuesday, if you guys just write colorful pictures all over on the test, it makes me happy, and I think, they know exactly what they're talking about. I didn't need to read this. I'm being sarcastic. Right? Some people don't appreciate it. I know, because I've read it in my evaluation. No, it's true. So is everybody okay on the mechanisms? All right. Yeah. It would be like a materialist. How about we go through examples of Michaelis kinetics? An example, just let's look at every Michaelis method we'll ever do. It can only be asked in about 2 or 3 different ways. It can be asked as a Lineweaver-Burke. It can be asked as, can you evaluate the Michaelis method plot and give an estimate on things? Okay, max, Kn, and so on and so forth. Or it can be, can you use the Michaelis-Menten equation and calculate what the velocity should be, initial velocity, if you know these variables, what's the Kn, if you know these variables. Those are the only ways you can really give questions, hard, you know, kind of calculated questions from Michaelis-Menten kinetics. So is everybody good with this? Yes.
How about the hydrophobic pocket and the oxyanion?
Oh, yes.
You have to show it?
Yeah, so if I asked for it, yes. But, so all of it, I said, every step, I said, oh, look at, this is very high energy, right? And the enzyme has to stabilize the energy. And so there's this important thing called the oxyanion hole, right? And it's basically a backbone amide, or several of them, that can associate with that and stabilize it, right? So that oxyanion hole is this hole in the pocket of the enzyme, right, that interacts with that oxygen and stabilizes that tetrahedral intermediate.
And that's all we have intermediate.
Yep, that's all, it's there to stabilize that.
So can we show that and not get knocked off at 20 points?
Oh, yeah, because I knock off 10 points when you do more than what you have. If I asked for the Oxyanion hole, yes, you would have to.
No, but if you do ask for it, we should draw it just like we did right now.
Yeah.
We'll be okay.
Yeah, I'm not good at three. How do you draw three? The oxyanion hole, the nitrogen from the oxyanion hole is actually part of the serine backbone. So how do you draw that, right? That's pretty crazy. That's why, you know, it's typically part of that serine, and then there are a few other amide backbones, backbone amides that also help with that. But that's all I care about. It's not about if you can draw, very well. It's about, do you get the nuts and bolts of all of this? You guys act like I'm like serious, graded. Okay. So are we good with that? Yeah, there's a glycine too. So
So would that be different if we did, like, if you said do an aspartate, would it cut in the opposite direction? Because
yes,
how you do it?
well, yeah, it would cut at the same position. It's just R2 would be less aspartate. Its specificity is different. So this brings up a good question. The specificity pocket for an aspartate would be here. So if this was, say, aspartate, the specificity pocket would be located at a different location. And, right, it cuts with aspartates, so it probably has in its pocket probably something like a lysine that could interact with it, right, and stabilize it. On the other hand, if we're talking chymotrypsin, what we would have is a deep hydrophobic pocket for chymotrypsin, right, where this R1 group would fit into that. So it's just a rearrangement really of the active site.
So it's not going to cut, they're all going to cut the
They're
same,
gonna cut, they're gonna,
regardless of what.
mechanism is mechanism. Yep. Specificity comes from specificity because of the molecular surface arrangement of
Audio
the
mic.
binding target.
Tina.
Specificity.
Right, so we're drawing that and, on the example of getting trypsin, can we put R1, for example, put a K for lysine, and what we go do have.
Do whatever the directions tell you. That's what I say. Do whatever the directions tell you. Now, this is an interesting point, just a second. One more thing in here. Do you think we could engineer, let's say we took trypsin, for instance, okay? Could we take chymotrypsin, right? And could we make it trypsin? Has the same reactive site, right? How could we make chymotrypsin trypsin? Yeah, we would just modify the specificity. And people do this. They take enzymes that have a specific substrate, and they're like, that's a cool reaction. I want it to do the reaction on this substrate. So what they try to do is modify the binding pocket, mutate amino acids, maybe make the binding pocket bigger. So where there are these big, bulky hydrophobic groups, like valine or isoleucine, they want to make the pocket bigger. What can they do? They can put something like alanine in that place. And what does that do? That puts a hole there where there was originally some atoms. If you make a smaller amino acid residue change, now you open up that pocket. So people do this kind of engineering. Nobody has the capability thus far of actually creating an enzyme from scratch. But what we can do is look at an enzyme and rationally re-engineer it to have specificity for different things. And I think that's really, really cool. Get way more information tonight than what you thought you were going to get, right? That's the way I guess I roll sometimes.
You will cut, thing was chymotrypsin, you will cut at lysine and arginine.
Yeah, if you could modify the binding pocket to provide specificity, change its specificity. So for instance, you have trypsin, which normally has, say, a negatively charged aspartate in the bottom of its binding hub. If you mutate that out to, say, a valine or something hydrophobic, potentially you could make it active towards hydrophobic residues. I know I skipped kind of off there, but you can, this is something we're able to do now. We can actually engineer enzymes, re-engineer them. Okay. More information on what you want to know, but going more
Using the equation.
Yep, yep.
This is zero to the straight from now.
We'll do all of it. We'll do all of it. Okay. So hopefully, I would say 50 to 60% of people that miss
Nothing.
questions
There's like a classroom
do not
video
know the
that
equation.
someone took of them doing a project that was in.
Right? And that might be funny. The question is, do you know your
No, I think it's anything
okay?
because it's in the
How
book.
do you know it?
Our book's
Most
there.
people that I see that miss points do it because they fail to
The third edition of the ecology book is like brand new.
Right?
And he's like
The
shoving it
initial
down our throats.
velocity, the initial rate of a reaction of an enzyme is equal to
Like
Vmax
my chapter 10, dude.
times
It's
the
like 10
substrate
pages.
concentration
And then in
divided
the second
by
edition,
the
but
Km
his
plus
chapter
the
10 slides
substrate
were 103
concentration. And
slides.
so what does this equation tell you? It tells you if you know 3 variables of any enzyme, you can determine the fourth, right? If you know the initial velocity, the Vmax, and the substrate concentration, you can determine the fourth variable, Km, right? If you know Km and Vmax and substrate concentration, you automatically can determine the initial velocity. This equation predicts the kinetics of an enzyme where 3 variables are known. Okay? And that's why it's so powerful. And we can use fitting programs where we only know a few of these parameters to actually determine these important parameters, Vmax and Km. So let's start with the Michaelis-Menten plot, and we'll work our way to this. How do we use this directly? Okay? So we said if we look at the initial rates of an enzyme at different starting substrate concentrations, this equation predicts that we will have a hyperbolic function, right? A hyperbolic function of the substrate concentration of the velocity. Okay? We can determine these Vmax and Km by inspecting the graph. We typically go slightly above. Okay, so let me draw in with my other marker so we can see that, so we don't get confused. Let's just draw in some numbers. This will be 2, 4, 6, 8, 10. And the velocity will be given in terms of millimolar per second. And that's the value. And so we can just inspect this. Okay, we go see where this is and imagine it going off infinitely long. It's going to be slightly higher than that. So we go above that line, and this, I erased it and then I redrew it. I'm on the ball with that, right? All right, this is Vmax. And in this class, I'll probably see about 4 or 5 different Vmaxes, right? It's an estimate. It's a visual inspection. So your Vmax is going to be different than my Vmax, but remember, it's higher than where those dots end. It's slightly higher. Going up to 10 is not cool. That's way too high. Okay? It's slightly higher. Okay? Yeah, I would guesstimate from this about 9. Okay? I would say Vmax is equal to about 9 millimolar per second. Okay? I would say that is Vmax from that. It's probably slightly less, but hey, ballpark, we're close. Okay, so that's Vmax. What is the definition of Km? Who can tell me what the definition is?
Oh, well, I had a question. For the initial velocity, is it always going to be millimolar per second?
No, it could change. It could be
Okay.
micromolar per
Would it
second.
be specific, like in the equation, if you're given things and you're wanting to find something with the units for V naught you given instead?
Yeah, you'll be given units. It will say there what unit it is. And so that has to be specified, or the velocity needs to not.
Will you ever, or will we ever get posed a question where we need to know the definition of Km, like the rates of?
Oh, the K minus one, yeah. Maybe. That's a good question. I'll have to think about that. I haven't written the exam yet, so you guys give me ideas. All right, so, okay.
Give him 50 ideas.
Then I'll be like,
Then he can't have
I
more.
gotta turn up the beat a little bit, right? I don't know about that. Okay, so K, what's the definition of K? Not the rate constants, right? What is it? It's those, yeah. So K minus 1 plus K2 over K1, right? No, that's not something I'll probably ask. If I did, the people that didn't show up today are all getting failed from. So, no, I'm not going to do that. It's an important thing to know, okay? Because it really tells you what the Km is. The Km is this understanding of how, the affinity that it has for its substrate. Okay. So that's how we look at this, right? We determine Vmax. Okay, Km, we go to 1/2 Vmax. It is not 1/2 Vmax. I've seen this over and over again. Km is not 1/2 Vmax. It is the substrate concentration at 1/2 Vmax. So if we went to say 4.5, right, which is half of 9, this is 1/2 Vmax. And we draw a line over to where that would hit the theoretical curve for this, right? If we were to extend these out, we would go down, straight down, right? And this is Km. It is the substrate concentration at 1/2 Vmax, okay? So let me put in some values here. So this is 1, 2, 3, 4, and substrate concentration, in this case is millimolar, right? We would be at a Km equal to about 1.5, right? Do not mess that up. If I see anybody in this room and I'm grading your exam, you mess that up, I'm going to take off extra points. Yes. You go into a special. All right. All right. So anyways, that's how we determine that. Okay, we can take this farther. Vmax is associated with how much enzyme there is, right? We know that small k, cat, the turnover number, right? The maximal rate that an enzyme can convert a substrate to product is equal to Vmax divided by the total enzyme concentration, ET, right, in the reaction. Okay? And so Vmax really doesn't tell you anything because you could be using different amounts of enzyme, right? And if you want to make an enzyme look faster, you just add more of it, and that will increase the Vmax. But in reality, if we want to know something about how fast an enzyme actually turns over its substrate into a product, we have to determine K-cat. In order to determine K-cat, you have to know enzyme concentration. So it has to be given. Okay? If it's not given, you can't determine this. Or if you're doing experiments, you have to know it, or else you cannot calculate it. so in this example, let me do an example. I say we have 1 micromolar equals total, right? Okay. So if I told you, well, look at this, evaluate it, tell me Vmax, Km, and Kcat, then what will we do? We would just take Vmax, which is in terms of millimolar per second. So we said that's 9 millimolar per second. And then we would divide it by E total. Now here's the point where everybody usually gets it wrong too. The units of concentration have to be the same. So we have 1 micromolar, but those are not the same units. So we have to convert. We have to say there are 1,000 micromoles per millimole, right? Micromolar per 1 millimole. Right? Because these have to cancel. So these cancel and these cancel. And I know that the concentration of enzyme technically isn't the same as the rate, but we do this by convention. We say that those cancel out because they are the same quantity values. Okay? So those cancel out. This is where we get our Kcat, right? And this would be given in terms of per second, per minute. It's always per unit time. And what it's telling you is each enzyme turns over the substrate to product this many times per second. That's how you can turn it. It's telling you a turnover. How many times does it crank out product per second? So I don't know what this is. What? 9,000? That's pretty good. That's a pretty fast thing. I can tell you that. So that's 9,000 per second. That's your K5. There's the other parameter, catalytic efficiency, which is equal to K cat over Km. If you haven't learned all these terms and what their equations are, I want you to make sure that you do that. Okay? It's probably going to be at least like a 10 to 15 points or something in the exam, at least, knowing these definitions, so you can apply them. Okay? So, we can do this, right? We've got our 9,000 per second, okay? Divided by our Km, which is 1.5 millimolar. What is that equal? It's like 6,000 per second per millimolar is how we usually do that. So per second per concentration, per unit time per concentration. And this really tells you efficiency. It allows you to compare one enzyme from another. Even though they do totally different reactions, you can compare their efficiencies to determine what is the better enzyme overall. Yes?
Could we, if we converted that to molar, would that be okay as long as it's the units that we have?
Yeah, units are, I don't care about units as long as the units are correct.
Okay.
When the units are incorrect, I get to be a harsh stickler, right? Okay, so we've gotten through that, right? Now, the question is, how do I use that without all of this? Okay, so you could ask a question, right? How do you use Michaelis-Menten equation? It probably wouldn't be worded that way, but it's a question where you have to use what you know about the Michaelis-Menten to determine some value. So, for instance, a question could be to provide you that substrate concentration is equal to 1 millimolar, Vmax is equal